Group 12, by modern IUPAC numbering, is a group of chemical elements in the periodic table. It includes zinc, cadmium and mercury. The further inclusion of copernicium in Group 12 is supported by recent experiments on individual copernicium atoms. Group 12 is also known as the volatile metals, although this can also more generally refer to any metal that has high volatility, such as polonium or flerovium. Formerly this group was named IUPAC as an old IUPAC system. The three Group 12 elements that occur naturally are zinc, cadmium and mercury. They are all widely used in electric and electronic applications, as well as in various alloys. The first two members of the group share similar properties as they are solid metals under standard conditions. Mercury is the only metal that is a liquid at room temperature, while zinc is very important in the biochemistry of living organisms. Cadmium and mercury are both highly toxic. As copernicium does not occur in nature, it has to be synthesized in the laboratory. Physical and atomic properties. Like other groups of the periodic table, the members of Group 12 show patterns in its electron configuration, especially the outermost shells, which result in trends in their chemical behavior. Group 12 elements are all soft, diamagnetic, divalent metals. They have the lowest melting points among all transition metals. Zinc is bluish-white and lustrous, though most common commercial grades of the metal have a dull finish. Zinc is also referred to in non-scientific contexts as spelter. Cadmium is soft, malleable, ductile, and with a bluish-white color. Mercury is a liquid, heavy, silvery white metal. It is the only common liquid metal at ordinary temperatures, and as compared to other metals, it is a poor conductor of heat, but a fair conductor of electricity. The table below is a summary of the key physical properties of the Group 12 elements. Very little is known about copernicium, and none of its physical properties have been confirmed except for its boiling point. Zinc is somewhat less dense than iron and has a hexagonal crystal structure. The metal is hard and brittle at most temperatures but becomes malleable between 100 and 150 degrees Celsius. Above 210 degrees Celsius, the metal becomes brittle again and can be pulverized by beating. Zinc is a fair conductor of electricity. For a metal, zinc has relatively low melting and boiling points. Cadmium is similar in many respects to zinc but forms complex compounds. Unlike other metals, cadmium is resistant to corrosion and as a result it is used as a protective layer when deposited on other metals. As a bulk metal, cadmium is insoluble in water and is not flammable. However, in its powdered form it may burn and release toxic fumes. Mercury has an exceptionally low melting temperature for a block metal. A complete explanation of this fact requires a deep excursion into quantum physics, but it can be summarized as follows. Mercury has a unique electronic configuration where electrons fill up all the available 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d and 6s subshells. Is such configuration strongly resists removal of an electron. Mercury behaves similarly to noble gas elements, which form weak bonds and thus easily melting solids. The stability of the 6s shell is due to the presence of a filled 4f shell. An F shell poorly screens the nuclear charge that increases the attractive Coulomb interaction of the 6s shell and the nucleus. The absence of a filled inner F shell is the reason for the somewhat higher melting temperature of cadmium and zinc, although both these metals still melt easily and, in addition, have unusually low boiling points. Gold has atoms with one less 6s electron than mercury. Those electrons are more easily removed and are shared between the gold atoms, forming relatively strong metallic bonds. Zinc, cadmium and mercury form a large range of alloys. Among the zinc-containing ones, brass is an alloy of zinc and copper. Other metals long known to form binary alloys with zinc are aluminium, antimony, bismuth, gold, iron, lead, mercury, silver, tin, magnesium, cobalt, nickel, tellurium and sodium. While neither zinc nor zirconium are ferromagnetic, their alloy ZrZn2 exhibits ferromagnetism below 35 K. Cadmium is used in many kinds of solder and bearing alloys, due to a low coefficient of friction and fatigue resistance. It is also found in some of the lowest melting alloys, such as Wood's metal. Because it is a liquid, mercury dissolves other metals and the alloys that are formed are called amalgams. For example, such amalgams are known with gold, zinc, sodium, and many other metals. Because iron is an exception, iron flasks have been traditionally used to trade mercury. Other metals that do not form amalgams with mercury include tantalum, tungsten and platinum. Sodium amalgam is a common reducing agent in organic synthesis and is also used in high-pressure sodium lamps. Mercury readily combines with aluminium to form a mercury-aluminium amalgam when the two pure metals come into contact. Since the amalgam reacts with air to give aluminium oxide, small amounts of mercury corrode aluminium. For this reason, mercury is not allowed aboard an aircraft under most circumstances because of the risk of it forming an amalgam with exposed aluminium parts in the aircraft. Chemistry. Most of the chemistry has been observed only for the first three members of the group 12. The chemistry of copernicium is not well established and, therefore, the rest of the section deals only with zinc, cadmium and mercury. Periodic trends. All elements in this group are metals. The similarity of the metallic radii of cadmium and mercury is an effect of the lanthanide contraction. So, the trend in this group is unlike the trend in group 2, the alkaline earths, where metallic radius increases smoothly from top to bottom of the group. All three metals have relatively low melting and boiling points, indicating that the metallic bond is relatively weak, with relatively little overlap between the valence band and the conduction band. Thus, zinc is close to the boundary between metallic and metalloid elements, which is usually placed between gallium and germanium, though gallium participates in semiconductors such as gallium arsenide. Zinc and cadmium are electropositive while mercury is not. As a result, zinc and cadmium metal are good reducing agents. The elements of group 12 have an oxidation state of +2, in which the ions have the rather stable D10 electronic configuration with a full subshell. However, mercury can easily be reduced to the +1 oxidation state, usually as in the ion Hg2+. Two mercury ions come together to form a metal-metal bond and a diamagnetic species. Cadmium can also form species such as 4-, in which the metal's oxidation state is +1. Just as with mercury, the formation of a metal-metal bond results in a diamagnetic compound in which there are no unpaired electrons, thus making the species very reactive. Zinc is known only in the gas phase in such compounds as linear zinc chloride, analogous to calomel. Classification. The elements in group 12 are usually considered to be D-block elements, but not transition elements as the D shell is full. Some authors classify these elements as main group elements because the valence electrons are in NS2 orbitals. Nevertheless, they share many characteristics with the neighboring group 11 elements on the periodic table, which are almost universally considered to be transition elements. For example, zinc shares many characteristics with the neighboring transition metal, copper. Zinc complexes merit inclusion in the Irving-Williams Williams series, as zinc forms many complexes with the same stoichiometry as complexes of copper, albeit with smaller stability constants. There is little similarity between cadmium and silver, as compounds of silver are rare and those that do exist are very strong oxidizing agents. Likewise, the common oxidation state for gold is +3, which precludes there being much common chemistry between mercury and gold, though there are similarities between mercury and gold, such as the formation of linear dicyano complexes minus. According to IUPAC's definition of transition metal as an element whose atom has an incomplete d subshell, or which can give rise to cations with an incomplete d subshell, zinc and cadmium are not transition metals, while mercury is. This is because only mercury is known to have a compound where its oxidation state is higher than +2 in mercury fluoride. However, this classification is based on one highly atypical compound seen at non-equilibrium conditions and is at odds to mercury's more typical chemistry, and Jensen has suggested that it would be better to regard mercury as not being a transition metal. Relationship with the alkaline earth metals. Although group 12 lies in the d block of the modern 18-column periodic table, the d electrons of zinc, cadmium, and mercury behave as core electrons and do not take part in bonding. This behavior is similar to that of the main group elements, but is in stark contrast to that of the neighboring group 11 elements, which also have filled d subshells in the ground state electron configuration but behave chemically as transition metals. For example, the bonding in chromium sulfide involves mainly the 3d electrons, that in iron sulfide involves both the 3d and 4s electrons, but that of zinc sulfide involves only the 4s electrons and the 3d electrons behave as core electrons. Indeed, useful comparison can be made between the properties and the first two members of group 2, beryllium and magnesium, and in earlier short-form periodic table layouts, this relationship is illustrated more clearly. For instance, zinc and cadmium are similar to beryllium and magnesium in their atomic radii, ionic radii, electronegativities, and also in the structure of the binary compounds and their ability to form complex ions with many nitrogen and oxygen ligands, such as complex hydrides and amines. However, beryllium and magnesium are small atoms, unlike the heavier alkaline earth metals and like the group 12 elements, and the periodic trends down group 2 from beryllium to radium are not as smooth when going down from beryllium to mercury due to the d block and lanthanide contractions. It is also the d block and lanthanide contractions that give mercury many of its distinctive properties. Compounds. All three metal ions form many tetrahedral species, such as McL2-4. Both zinc and cadmium can also form octahedral complexes such as the aqua ions 2+, which are present in aqueous solutions of salts of these metals. Covalent character is achieved by using the s and possibly p orbitals. Mercury, however, rarely exceeds a coordination number of 4. Coordination numbers of 2, 3, 5, 7 and 8 are also known extensions. Although copernicium is the heaviest known group 12 element, there has been some theoretical work regarding possible heavier group 12 elements, although a simple extrapolation of the periodic table would put element 162 unhexaBm under copernicium. Relativistic Dirac-Fock calculations predict that the next group 12 element after copernicium should actually be element 164 unhexaquadium, which is predicted to have an electron configuration of 5 grams 18,6 F 14,7 D 10 8 S 28 P 1 22. The 8s and 8p1/2 orbitals are predicted to be so strongly stabilized relativistically that they become core electrons and do not participate in chemical reactions, unlike the earlier group 12 elements where the s electrons behave as valence electrons. However, the 9s and 9p1/2 levels are expected to be readily available for hybridization and bonding, so that unhexquadium should still behave chemically like a normal transition metal. Calculations predict that the 7d electrons of unhexquadium should participate very readily in chemical reactions, so that unhexquadium should be able to show stable +6 and +4 oxidation states in addition to the normal +2 state in aqueous solutions with strong ligands. Unhexquadium should thus be able to form compounds like UHQ4, UHQ4, and UHQ2-2, which is very different behavior from that of lead, which unhexquadium would be a heavier homologue of if not for relativistic effects. Nevertheless, the divalent state would be the main one in aqueous solution, and unhexquadium should behave more similarly to lead than unhexquadium and unhexquadium. Unhexquadium should be a soft metal like mercury, and metallic unhexquadium should have a high melting point as it is predicted to bond covalently. It is also expected to be a soft Lewis acid and have Arlen's softness parameter close to 4 electron volts. It should also have some similarities to an unoxylam as well as to the other group 12 elements. Unhexquadium should be at most moderately reactive, having a first ionization energy that should be around 685 kilojoules per mole, comparable to that of molybdenum. Due to the lanthanide, actinide, and superactinide contractions, unhexquadium should have a metallic radius of only 158 pm, very close to that of the much lighter magnesium, despite its being expected to have an atomic weight of around 474 U, about 19.5 times as much as that of magnesium. This small radius and high weight cause it to be expected to have an extremely high density of around 46 grams cm-3, over twice that of osmium, currently the most dense element known. At 22.61 grams cm-3, unhexquadium should be the second most dense element in the first 9 periods of the periodic table, with only its neighbor unhextrium being more dense. Metallic unhexquadium should be quite stable, as the 8s and 8p1/2 electrons are very deeply buried in the electron core and only the 7d electrons are available for bonding. Metallic unhexquadium should have a very large cohesive energy due to its covalent bonds, most probably resulting in a high melting point. Theoretical interest in the chemistry of unhexquadium is largely motivated by theoretical predictions that it, especially the isotope 482 UHQ, would be at the center of a hypothetical second island of stability. History. The elements of Group 12 have been found throughout history, being used since ancient times to being discovered in laboratories. The group itself has not acquired a trivial name, but it has been called Group IIB in the past. Zinc. Zinc has been found being used in impure forms in ancient times as well as in alloys such as brass that have been found to be over 2,000 years old. Zinc was distinctly recognized as a metal under the designation of Fasada in the medical lexicon ascribed to the Hindu king Madanapala and written about the year 1374. The metal was also of use to alchemists. The name of the metal was first documented in the 16th century, and is probably derived from the German zinci for the needle-like appearance of metallic crystals. The isolation of metallic zinc in the West may have been achieved independently by several people in the 17th century. German chemist Andreas Markgraf is usually given credit for discovering pure metallic zinc in a 1746 experiment by heating a mixture of calamine and charcoal in a closed vessel without copper to obtain a metal. Experiments on frogs by the Italian Dr. Luigi Galvani in 1780 with brass paved the way for the discovery of electrical batteries, galvanization and cathodic protection. In 1880, Galvani's friend, Alessandro Volta, invented the voltaic pile. The biological importance of zinc was not discovered until 1940 when carbonic anhydrase, an enzyme that scrubs carbon dioxide from blood, was shown to have zinc in its active site, cadmium. In 1817, cadmium was discovered in Germany as an impurity in zinc carbonate minerals by Friedrich Strohmeyer and Carl Samuel Lebrecht Hermann. It was named after the Latin cadmia for calamine, a cadmium-bearing mixture of minerals, which was in turn named after the Greek mythological character Kappa Alpha Delta Mu Omicron Sigma Cadmus, the founder of Thebes. Strohmeyer eventually isolated cadmium metal by roasting and reduction of the sulfide. In 1927, the International Conference on Weights and Measures redefined the meter in terms of a red cadmium spectral line. This definition has since been changed. At the same time, the International Prototype Meter was used as standard for the length of a meter until 1960, when at the General Conference on Weights and Measures the meter was defined in terms of the orange-red emission line in the electromagnetic spectrum of the krypton-86 atom in vacuum. Mercury has been found in Egyptian tombs which have been dated back to 1500 BC, where mercury was used in cosmetics. It was also used by the ancient Chinese who believed it would improve and prolong health. By 500 BC, mercury was used to make amalgams with other metals. Alchemists thought of mercury as the first matter from which all metals were formed. They believed that different metals could be produced by varying the quality and quantity of sulfur contained within the mercury. The purest of these was gold, and mercury was called for in attempts at the transmutation of base metals into gold, which was the goal of many alchemists. Hg is the modern chemical symbol for mercury. It comes from hydrogerum, a Latinized form of the Greek word upsilon delta rho alpha rho gamma upsilon rho omicron sigma, which is a compound word meaning water silver, since it is liquid like water and shiny like silver. The element was named after the Roman god Mercury, known for speed and mobility. It is associated with the planet Mercury. The astrological symbol for the planet is also one of the alchemical symbols for the metal. Mercury is the only metal for which the alchemical planetary name became the common name, copernicium. The heaviest known group 12 element, copernicium, was first created on February 9, 1996, at the Gesellschaft-für-Schwerionenforschung located in Darmstadt, Germany by Sigurd Hoffmann, Victor Ninoff et al. It was then officially named by the International Union of Pure and Applied Chemistry after Nicolaus Copernicus on February 19, 2010, the 537th anniversary of Copernicus's birth. Occurrence. Like in most other D-block groups, the abundance in Earth's crust of group 12 elements decreases with higher atomic number. Zinc is with 65 parts per million the most abundant in the group, while cadmium with 0.1 ppm and mercury with 0.08 ppm are orders of magnitude less abundant. Copernicium, as a synthetic element with a half-life of a few minutes, may only be present in the laboratories where it was produced. Group 12 metals are chalcophiles, meaning the elements have low affinities for oxides and prefer to bond with sulfides. Chalcophiles formed as the crust solidified under the reducing conditions of the early Earth's atmosphere. The commercially most important minerals of group 12 elements are sulfide, sulfide minerals. Sphalerite, which is a form of zinc sulfide, is the most heavily mined zinc-containing ore because its concentrate contains 60 to 62% zinc. No significant deposits of cadmium-containing ores are known. Greenite, the only cadmium mineral of importance, is nearly always associated with sphalerite. This association is caused by the geochemical similarity between zinc and cadmium, which makes geological separation unlikely. As a consequence, cadmium is produced mainly as a byproduct from mining, smelting, and refining sulfide ores of zinc, and, to a lesser degree, lead and copper. One place where metallic cadmium can be found is the Viliwi River basin in Siberia, although mercury is an extremely rare element in the Earth's crust, because it does not blend geochemically with those elements that constitute the majority of the crustal mass. Mercury ores can be highly concentrated considering the element's abundance in ordinary rock. The richest mercury ores contain up to 2.5% mercury by mass, and even the leanest concentrated deposits are at least 0.1% mercury. It is found either as a native metal or in cinnabar, corduroy, livingstonite and other minerals, with cinnabar being the most common ore, while mercury and zinc minerals are found in large enough quantities to be mined. Cadmium is too similar to zinc and therefore is always present in small quantities in zinc ores from where it is recovered. Identified world zinc resources total about 1.9 billion tons. Large deposits are in Australia, Canada and the United States, with the largest reserves in Iran. At the current rate of consumption, these reserves are estimated to be depleted sometime between 2027 and 2055. About 346 million tons have been extracted throughout history to 2002, and one estimate found that about 109 million tons of that remains in use. In 2005, China was the top producer of mercury with almost two-thirds global share, followed by Kyrgyzstan. Several other countries are believed to have unrecorded production of mercury from copper electrowinning processes and by recovery from effluents. Because of the high toxicity of mercury, both the mining of cinnabar and refining for mercury are hazardous and historic causes of mercury poisoning. Production. Zinc is the fourth most common metal in use, trailing only iron, aluminium, and copper, with an annual production of about 10 million tons. Worldwide, 95% of the zinc is mined from sulfide ore deposits, in which sphalerite is nearly always mixed with the sulfides of copper, lead and iron. Zinc metal is produced using extractive metallurgy. Roasting converts the zinc sulfide concentrate produced during processing to zinc oxide. For further processing, two basic methods are used: pyrometallurgy or electrowinning. Pyrometallurgy processing reduces zinc oxide with carbon monoxide at 950 degrees Celsius into the metal, which is distilled as zinc vapor. The zinc vapor is collected in a condenser. Electrowinning processing leaches zinc from the ore concentrate by sulfuric acid. After this step, electrolysis is used to produce zinc metal. Cadmium is a common impurity in zinc ores, and it is most isolated during the production of zinc. Some zinc ores concentrates from sulfidic zinc ores contain up to 1.4% of cadmium. Cadmium is isolated from the zinc produced from the flue dust by vacuum distillation if the zinc is smelted, or cadmium sulfate is precipitated out of the electrolysis solution. The richest mercury ores contain up to 2.5% mercury by mass, and even the leanest concentrated deposits are at least 0.1% mercury, with cinnabar being the most common ore in the deposits. Mercury is extracted by heating cinnabar in a current of air and condensing the vapor. Super-heavy elements such as copernicium are produced by bombarding lighter elements in particle accelerators that induces fusion reactions, whereas most of the isotopes of copernicium can be synthesized directly this way. Some heavier ones have only been observed as decay products of elements with higher atomic numbers, 112 Cn plus N in total. Approximately 75 atoms of copernicium have been prepared using various nuclear reactions.